Thank you for joining us on Synthesis Workshop. My name is Andy Tran, a member of the Synthesis Workshop editorial team. Today, we are joined by Rahul Giri for another Research Spotlight episode. Rahul completed his Bachelor's degree of Science in 2016 at Acharya Narendra Dev College. Following this degree completion, he moved to complete a master's degree in 2021 with Professor Alakash Desai, focusing on complex molecule synthesis. He currently is at the University of Bern with Professor Dmitry Katayev, focusing on developing methodologies for functional group transfer reagents and nitrating reagents. Thanks a lot for joining us, Rahul.
Hello everyone, my name is Rahul Giri and I would like to start by thanking the Synthesis Workshop for the opportunity to present my latest research. I am currently working in the lab of Professor Dmitry Katayev at the University of Bern, where we focus on the synthesis of small molecules using advanced techniques like photoredox catalysis and electrochemistry. Today I will be discussing our latest work on dual functional group transfer reagents, which is a key area of our research. Our goal is to develop efficient methods for transferring functional groups to different molecular scaffolds, which enables the synthesis of complex compounds with high precision. I will also look forward to share our findings in future and also in the comment section and engaging with you all during the workshop. Research at the Katayev lab involves different fields such as fluoroalkylation, where we focus on the CX bond activation of commercially available reagents such as acids, anhydrides, and ketones. We involve iridium photocatalyst to do switchable divergent synthesis. The next area where our lab is working actively is on nitration chemistry. We try to achieve a safer nitration mode using functional group transfer reagents again. But finally, what I will discuss today is our recent work on dihalogenation, where we have developed a novel functional group transfer reagents based on such cores. This approach uses a single reagent to achieve heterodihalogenation, representing the first example of such a transformation. And also, we will study the mechanism in details. The functional group transfer reagents are simple. There is a functional group installed over a core. They are known as monofunctional transfer reagents because there is only one functional group transfer attached over a core. Upon activation, these monofunctional group transfer reagents are susceptible to release a functional group intermediate. These intermediates can be carbocation, carbanion, or radicals. These reactive species then get trapped over an acceptor to make the desired product. Since beginning of the chemistry, these type of reagents are being designed. For example, I will take N-chlorosuccinamide. These N-chlorosuccinamides are historically being used for chlorine transfer. But why do we need N-chlorosuccinamide? If we have chlorine, if we have HCl, if we have chlorine salts. The reason being the transfer of one atom of chlorine over succinamide make it stable, safer, and practical to use for diverse array of applications. Therefore, on this principle, there are multiple functional group transfer reagents has been designed. For example, the Chen's reagent, Z transfer reagent, amine transfer reagent by Buchwald. Our group also developed a nitro group transfer reagent. Then Antonio Toni group developed a trifluoromethylation reagent or a trifluoromethoxylation reagent. Recently, Baran Group has developed anomeric amines to transfer the chlorine and bromine atoms. Similarly, many feedstock chemicals are also being used for transfer of the crucial functional groups such as trifluoromethyl group by Stephenson and West, as you can see. Innovative designs to transfer two functional groups at a time. We call it dual functional group transfer reagents. In the dual functional group transfer reagents, there is a core which is being attached to two functional groups, and upon activation, there is a release of core due to some sort of driving forces, and the acceptor molecule accepts both of the functional group to make their desired product having two functional groups. The key examples include the recent development by Zhu Group, where they can transfer SO2 pH and SCF3 molecules onto an acceptor. The Glorious group has made significant developments in this field, and I highly recommend to read these Nature Reviews chemistry from the same group, where they have really discussed in a detail what are the bifunctional reagents or dual functional group transfer reagents. Then Morandi group made a development in the field of subtle catalysis using dihaloalkanes to transfer these X2 groups over olefins. Our group has also made a contribution in this field by using anhydrides to make cyclic gamma lactones and gamma lactams using switchable divergent concept. Then Oestreich group came up with an innovative strategy to make dual transfer based on an oxime core. I will give you two proper examples from the literature where the monofunctional group transfer or difunctional group transfer has been done. The one example is from our group where we can do a terminal nitration of olefins and then release the succinamide core using monofunctional group transfer N-nitrosuccinamide reagent. While the Morandi group used electrochemistry to do the subtle of dibromine compounds using electrochemistry. With these research, I think I made a solid background of what are the concepts of the functional group transfer reagents. Moving on to our current research, I will try to highlight the most of the halogenating reagents till now in the literature. There might be some missing reagents, but these are the most useful and widely used reagents in the literature. So to start with, there are molecular halogens. They can do multiple jobs to functionalize different type of hydrocarbons. While they have excellent applications, but they lack in selectivity, they have oxidizing properties, and they are very difficult to handle. That's why people have developed a series of halogenating reagents such as hydrogen halides, hypochlorites, metal halides, for example. Now, West Group has also showcased that they use TMS chloride as a selective chlorine source. While nitrogen trichloride, tetrabutyl ammonium halides, these are the known sources to transfer any halogen molecules onto hydrocarbons. Then the N-centered reagents are developed such as NBS and NCS, DCDMH, TCCA, and not to forget, significant contribution is done by the Baran group where they used such NCl bonds to transfer the chlorine, where anomeric amides are used. Recently, Han group has developed such molecules based on imine core to transfer the X molecule, and they have extensive scope. This paper is still on Chem Archive. I recommend to read it. While CFBSA has been used to install chlorine, and dichloramine T is also being used for a very long time in literature. Then, as we discussed previously, oxime-based surrogates were used by Oestreich group, then sulfuric chloride or Snyder group has made excellent developments in the field of asymmetric halogen transfer and so on. Then there are C-centered radical. Very recently, McNeil and co-workers, they have showcased that they can decompose PVC to make a chlorine transfer reagents, and that is quite impressive. Diethyl alpha-alpha dibromomelonates are used sometime, and then there are very minor instances where such acetyl chloride, oxalyl halide, or hexachloroethane has been employed for making functionalization of hydrocarbons. As discussed, Morandi group has made significant contribution. Then Giri group from USA in Pennsylvania, they have developed alpha bromoacetate in 2024, just before this publication, and they showcased that they can do dihalogenation of alkenes in a very facile way using just light. Then eye-centered reagents are popular, not to mention this reagent which is being used by Gilmer and other TTC-based reagents. What is very interesting in such works that they are often used for one class of compounds. For example, they are being used for either olefins or alkynes or aromatic compounds. But what we were trying to do to make a general reagent to do any type of halogenating chemistry which involves chlorine or bromine transfer. Therefore, we developed reagents based on chalcone core and we employed such molecules to do dichlorination, and then we selectively did bromochlorination as discussed in the first slide, that we can really install two type of functional groups from one molecule and we can do heterodihalogenation. And then we also use dibrominating reagents such as based on cinnamic acid cores or also on the chalcone cores. With that, I will move on to where the inspiration of this story comes from. So the inspiration is taken from my beginning of the PhD work where I was trying to activate anhydrides using photoredox conditions. In this work, we did CCl bond activation and we transferred this gem difluororadical onto this olefin, and then a second cyclization takes place and we made gamma lactones. The idea is simple, that once you excite this iridium-3, it goes to the excited state and it's a good reductant, and it transfers one electron onto this anhydride, which goes to anion state, and then you form a radical. This radical attacks on the olefin in a Giese type reaction and then forms an alkyl radical. This alkyl radical is susceptible to oxidation and you form a carbocation. This carbocation undergoes intramolecular cyclization to yield lactone. But what I want you to focus on is this step, where you reduce this CCl bond adjacent to carbonyl, which is the basis of the whole work. And I will tell you in the next slide how this work inspired the reagent design and how we implemented it. In the previous slide, I have showcased that Morandi group has demonstrated the activation of dihaloalkanes. They contain very strong CX bonds, and that's why they need electrochemistry to provide higher activation energy. That's why they are less reactive. But on the other hand, if you see cyclohexadiene cores, they are also useful to release two functional groups. In these type of cores, they are unstable and they are sometimes very hard to access because the origin lies in installing two functional groups over a aromatic compound. That makes it complicated. That's why in between of these very high reactive compound and very stable compound, we wanted to design something which is in between of these, and then we can explore the lower reactivity than the cyclohexadiene core and higher reactivity than the dihaloalkane core. In terms of accessibility, most of the reagents of dihaloalkane core you will find it commercially, but for the cyclohexadiene core, it's very hard to obtain. So in we have to manage, and we wanted to bridge the gap between the reactivity and accessibility. That's why we designed such type of core to develop two functional group transfer at a time. Based on the principle which were stated before, we designed a reagent based on cinnamic acid core, and then we found that indeed it is transferring two chlorine atoms to the styrene molecule under photoredox condition. So this was our initial results, and then we received a minimal amount of product, but based on that we started our optimization. And during optimization we found that A and B were not susceptible to our reaction conditions, while C and D did not react at all. And when we were screening the reagents, we found that F is quite impressively reacted and transferred two chlorine atoms under the similar conditions. The reagents based on chalcone core were perfect for our reaction. Then we also scaled the reagent preparation on 60 gram scale, and it was quite cheap for us. And we also tried to differentiate the electronics on the aromatic part, and then we found reduced yield. That's why we stuck with H, and based on chalcone, we designed the reagents for chlorobromination and others as well. Learning that chalcone cores are suitable We also found that in our reaction condition, the selective chlorine-bromine was transferred using such a chalcone core. Similar results were obtained for the dibromination reaction using chalcone-based reagents, but since this cinnamic acid reagent was commercially available, so we choose to do all of our reactions using cinnamic acid core for dibromine transfer. We did optimize the reaction conditions and we found that we can achieve transferring dichlorine molecule on the styrenes. Some sensitive functional groups were also tested, and I will not go into details of the scope, but as you can see, multiple fluorinated molecules installed over a styrene, they are well tolerated. Not only terminal styrenes, non-terminal styrenes were working, cyclic styrenes and non-activated compounds were well tolerated. But what I want to emphasize here is that this dihydrocholesterol molecule, which is in its native form, unprotected alcohol, tolerates very well, and we get a reasonable amount of product. While allenes were also good in our reaction condition. So based on that, this reagent is quite good to functionalize olefins and allenes in a very general way. The highlight of this work is this slide, where we can do cross halogenation reaction and we can choose either olefin or allenes, and we can regioselectively get bromine installed here and chlorine on the benzylic position, for example. And then allenes are also very regioselective and other regioisomers we don't form. So after optimization, we received it in a decent yield, and then this molecule is very interesting because it has 4 halogen atoms installed onto it, and then this protocol selectively functionalized styrenes, non-styrenes, allenes, and several late-stage functionalizations were demonstrated in the scope of the reaction. Onto making the scope of the olefins, and we found that olefins and also alkynes and allenes or bicyclobutanes, they were all tolerated under the standard reaction conditions to furnish such molecules using dihydrocinamic acid bromine reagent. With this reagent, our reaction product yields was very nice, and we can also go to densely functionalized alkenes, and such sensitive groups like silyl myotiatas are well tolerated. When we move to alkynes, we can also see that free alcohols were giving the product in a decent yield with a very high E to G ratio. Carbon are an example where an electron poor double bond kept intact while the electron rich double bonds reacted exclusively, providing the dibrominated product in 1:1 ratio. There are also reports where such brominated compounds are being used as flame retardants, and this is an actual flame retardant, and we can achieve this molecule under our standard condition in 20:1 DR. Allenes gave exclusively such molecules. Since recent attention has been shifted to bicyclobutanes because people are taking advantage of strain in these systems, and then these bicyclobutanes are being prepared in multi-step synthesis, and there is one report where they prepare in one pot. But the thing is that we tried to improve this method by using three-step protocol and doing just one column to produce such a molecule. This is a method which is being developed in our lab and has been tested by several master and bachelor students, and we always get this yield of whatever is reported in the paper. So try this protocol for making such a sulfone-based bicyclobutanes. Then we used bicyclobutanes to release the strain of these bicyclobutanes, and we formed such molecules in decent yields and decent distereoselectivity. Encouraged by the successful application of the dual functional group transfer reagents on dihalogenation, we attempted to understand the mechanism of the reaction by a combination of experimental and spectroscopic investigation. Together with the density functions theory, we better understood the mechanism operative in our case. To better illustrate the sequence of the reaction, we selected the bromochlorinating reagent as a reference reaction to study the mechanism. We established from UV visible studies that the iridium PPY3 is the only species which is being absorbed at 440 nanometer. CV experiments revealed that these CBr bond and CCl bonds are susceptible to be reduced by iridium 3 start. And with that, the reaction sequence starts. The first reaction takes place at this carbonyl center and this is reduced to a radical anion. The mesolytic cleavage provides intermediate 1 and bromine ion, which undergoes a 1-2 rearrangement and form a 3-membered ring like that. After this 1-2 rearrangement, which is also known as halogen dance, a radical intermediate 2 is formed, which is able to be oxidized by the iridium 4 excited state. And the restoration of photocatalyst takes place. After that, the released bromine ion can generate the reagent again, but with the opposite regioselectivity. And this was indeed happening in our reaction condition, which was evident by the time resolved carbon 13 NMR. We saw that after 30 minutes, the reagent K is being converted to K prime, and this also shows us that now this K prime can operate on the same pathway. But to go a step back, and we see that this Br negative can take a chlorine positive and make a BrCl molecule, which is a key species in our reaction mixer. And after that, the same type of event takes place on K prime and intermediate 4 is generated, then 1 to halogen shift to generate intermediate 5, which can be converted into intermediate 6 after oxidation. This intermediate 6 again can trap a chlorine negative and then goes to K. So as you can see from the mechanism, we catalytically release BrCl, which is an active species to functionalize hydrocarbons. What other evidences we have to say this? Because we did the regioselectivity test. So we prepared a reagent which has BrCl and the opposite stereochemistry Cl and Br. And what we found that the only product which is being formed is bromine at the beta position and chlorine at the alpha position of the styrene. We never saw the opposite regiochemistry in this case. And also we did crossover experiment by using KBr and found that if there is a bromine ion present in the reaction mixture, we can also get ClCl or BrCl product. But again, we never saw chlorine and bromine switch. After that, we studied the mechanism of the attack of the BrCl molecules or the active species. So we saw that if you do the non-classical carbocation shift, clear evidence that a polar mechanism is operative, while the phenonium ion shift indicated the same thing, that we generate a polar species such as Br2, BrCl or Cl2 in the reaction mixture, which further reacts with the olefin. With that, I would like to take an opportunity to thank the people involved in this work, and especially to my thesis supervisor, Professor Dmitry Katayev, for providing me the opportunity to work in his lab, and then our collaborators. And special thanks goes to Igor for making this work possible, Dr. Anthony and Subrata, Matthias. These people helped me a lot during this work. And I would like to thank the whole Katayev lab, funding agencies, University of Bern, and follow us on LinkedIn and Twitter. With that, I would like to thank again the Synthesis Workshop for providing me the opportunity, and thank you all for listening. Thank you very much and have a nice day.
Thank you for tuning in to this installment of our Advanced Organic Chemistry series, and thank you, Rahul, for sharing your exciting research with us. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments that you have. Follow us on Twitter to stay up to date, and we'll see you all next time.